All right, let's start relatively on time because I know everyone will want to get lunch on time. Welcome back and welcome to the second session on types. So to start us off, we have a talk on Quotient Haskell, lightweight quotient types for all, and Brandon will be giving the talk.
Hopefully I'm, okay, it seems like I'm audible. Okay, great. So I'm going to be talking today about Quotient Haskell. For those that are familiar with Liquid Haskell, this is an extension of that. It extends the refinement type system of Liquid Haskell to add support for quotient types. Lightweight here, meaning lots of the heavy lifting, the manual proof obligations that typically come with quotient types are automatically verified for you. Okay, so to begin with, I'm going to jump straight into an example here. And I'll jump straight into a very simple example of natural numbers, defined here two different ways. One is a subtype, pretty traditional way of doing it, and the other is as a quotient type. In both cases, the underlying type here are the integers. So with subtypes, if I can click next. With subtypes, we attach a predicate or a refinement to some underlying type that constrains how terms of that type can be constructed. Meanwhile, with quotient types, we attach equations or quotients to an underlying type that describe how terms of that type can be eliminated. I'll get into a little bit more detail about what that means in just a moment. But first of all, I'm going to start with a little bit of motivation here behind why you would even want subtypes or quotient types in your type system. In both cases, you're going to add expressivity to the type system. You're going to be able to express a wider range of properties and have them checked statically for you. So with subtypes, as I said earlier, terms can be constrained as to how they can be constructed. And for quotient types, you can constrain how they can be eliminated. Okay, so I'm going to describe now a little bit by what that means through an example. Again, I'm sticking with the natural numbers here, keeping it relatively simple. And I'm going to start with construction. So you see this, I've started with an addition function here. And I have this addition function that says, OK, if I add two integers together, I get a natural number. This is, of course, absolutely nonsense if natural numbers are defined as a subtype. This is not going to type check. If you try to type check this in Liquid Haskell, it certainly won't type check, as you should hope. But for elimination, well, every natural number is an integer, right? So this will type check, and there's not really anything to do here because every natural number is just an integer by the subtyping rule. OK, so in contrast, now we're going to look at natural numbers defined by means of a quotient type. So now this same addition function that takes two integers and constructs a natural number, now this is perfectly fine. This is perfectly fine. There's nothing to check. In this case, it's because every integer is a natural number if you define natural numbers as a quotient type. However, in this circumstance instead, this one doesn't type check. And this one doesn't type check because you cannot prove that you're sign invariant here because you're actually going to end up trying to recover the sign by going back into integer, and this is a problem. So this one doesn't type check. So that's the difference between the two. It's a very simple example here, and it's part of the duality between quotient types and subtypes. OK, so what is the problem with current implementations of quotient types? Well, arguably, there's not a huge problem with how they're implemented in different languages, and they're implemented in that way for certain reasons. So for example, in proof assistants like, say, cubical Agda, which has quotient inductive types, actually having manual proof obligations isn't really a big problem because the proofs themselves are just terms that you want the content of in many different cases. However, in the context of something like Liquid Haskell, where I'm extending Liquid Haskell with quotient types, suddenly this doesn't make as much sense anymore. The proof content isn't so important, and suddenly the manual proof obligations just become a bit of a burden and a hurdle to practical use. OK, so in this talk, I'm going to introduce Quotient Haskell, which is Liquid Haskell plus quotient types. I'm focusing here on the system to make some of the key ideas easier to understand, rather than focusing on things like the core language or some of the typing rules. OK, so our approach is going to be presented in 4 parts. The syntax of the quotient types in Quotient Haskell, generation and checking of respectfulness theorems, which are the fact that functions obey quotients, and then the introduction of the equalities themselves back into the refinement logic, because just having checks isn't enough. You actually need those equalities to become realized in the logic some way. And finally, I'm going to discuss some of the subtyping rules for quotient types that allow you to more easily reuse certain components of your code. OK. So I started with the example of natural numbers. Now I'm going to actually use an inductive example here. I'm going to explain how all of this works in a moment. So I'm going to use the inductive example of mobiles, named after the ornament that turns. And these things are binary commutative trees, where they're invariant with respect to permutations of the branches. So you see here I have an underlying type of binary trees, and then I have this swap equality constructor that allows you to state that you can permute branches. OK, so specifically, Quotient Haskell supports quotient inductive types, which is a specific class of quotient types. Again, I'll describe that a little bit more in a moment. So here you can see, OK, like everything in Liquid Haskell, these things are defined in these blocks. They look like kind of little comment blocks with little @ symbols. It's a refinement of a type. So first of all, you start with a normal type, quotient type declaration. It's the same as a normal data declaration here. You can add type variables. Then you give an underlying type. This is the base underlying type that forms the data of the quotient type. And then you follow it up with this symbol here, which is very much like the separator for data constructors, except with a little division-like symbol there to correspond to quotienting. And you specify these equality constructors. And these things are built, first of all, you can quantify them by variables. You can also quantify by preconditions. I'll not describe that here, simply to keep this example simpler. You can find more details about how these preconditions behave in the paper. Both sides of the target equality have to have the correct type, and this correct type should be type mobile A, which might seem like a problem right now if you look into it in a bit of detail, but I'll describe how that works in a second. OK. So as I said, Quotient Haskell implements quotient inductive types. This means that the equality constructors are defined, typically this means that equality constructors are defined mutually alongside the data constructors. So for example, if we consider the swap equality constructor here and you really think about the type, there's a bit of a problem here in that the bin data constructor is claiming to be able to take two mobiles and construct a new mobile. Now, of course, that's not the typical type for a bin that we would have from the definition of trees. And in fact, we have to add a new typing rule for bin to allow for this. And this is OK because we should expect that bin respects a swap equality constructor by definition in this circumstance. So, but if we add a new typing rule, we also have to resolve the type ambiguity, which Quotient Haskell handles based on when you're applying bin to different types. OK. OK. So here's an example of how you construct a new type for bin. So we can take the typical type here of bin. We then find all of the strictly positive occurrences of tree that happen to where the type arguments here unify with the type arguments applied in the underlying type of mobile, which here happens to be a free variable, so this is fine. So in this circumstance, we find all of these suitable positions. Then we apply, in this case, the unifier is trivial. So you just create this type here at the end. And now we have a bin data constructor. We have a new type for it. And you have to pick one or the other type based on what you're applying bin to. This is a bit different to the typical approach for quotient types, or if you see quotient inductive types, how the approach normally works, say in something like cubical agda. This is a little bit different because we're actually taking some underlying type and changing the types of its data constructors. And the reason we do this is because it makes subtyping a lot easier to work with, and it makes these implicit coercions, for example, from a tree into a mobile. You don't have to do anything. Every tree is a mobile. OK, so I'm going to talk a bit about respectfulness terms. So this is a very critical component of quotient types, is the fact that their quotient should be respected by any function that's defined on them. So again, we're sticking with the mobiles example. We start with the swap equality constructor here, and we take a look at the summation function. And then we think, OK, does this summation function respect swap? What does that mean? Well, it means that this respectfulness term holds. And the way that you can think about this is you can see, if you take the left-hand side of the target equality of swap, you find out which one of the patterns of sum that it applies to. and then you substitute in the variables. And you realize that this is a respectfulness theorem that you get out. Okay, I've missed out the universal quantification here, just to keep it simpler. But this is the end respectfulness theorem. And this is then passed to, in this case, the SMT solver along with every other constraint generated by Liquid Haskell. So this is just automatically verified for you. And this is absolutely something that Liquid Haskell will automatically verify for you. So, okay. So introduction of actually quotient equalities back into the refinement logic. How is this done? Because, okay, so we've checked that the equalities hold for all functions, but we actually don't have the equalities that we can make use of to prove new things in our type system. So how do we introduce this? So now I'm going to consider a slightly different function from the summation function. I'm going to consider the map function on mobiles. So something you might notice here is that this map function, we have a bit of a problem. And that is because if you want to show that map respects the swap equality constructor, we're going to need to use swap inductively here in the proof. And we can only do that if swap is somehow available to us within the logic. So the way that this is addressed is there's a particular rewriting algorithm built into Quotient Haskell that makes use of the equality constructors to rewrite equations between terms of a quotient type into a sequence of disjunctions. Okay, so the final step here is the subtyping rules. Go back. The subtyping rules. So with subtyping, there's a few different properties that I want. One key property is that for some underlying type, its terms should be elements of all of the quotient types built on top of it. And this should happen in a hierarchy too. So for example, again, every tree is a mobile in this circumstance. And again, this is just an implicit thing that is checked because of the subtyping rule. Okay, so then we have this extra, more complex subtyping rule, which I haven't described in too much detail here. And this follows that if given two quotient types, if one underlying type is a subtype of another, and for each of its quotients, there's another quotient that's a subquotient of the other, then it becomes a subtype of the other one. So you can have, for example, two different quotient types with one quotient that subsumes another, and you get a subtyping relation between them that's automatically verified for you. And, yeah. So I'm not going to describe the subquotienting relation. Again, you can check the paper for more details about how that's defined. Okay. So some other examples include rational numbers. These are all things I've checked in Quotient Haskell, so modular arithmetic, bags of mode sets, polar coordinates, permutable n-ary trees, which is similar to mobiles, but extended to the n-ary case, languages of equations, for example, you can equip the lambda characters with eta, lol, or free algebraic structures that you wouldn't normally be able to define. Okay, so some areas of further work that some of these I've begun to look at, and some of them I haven't addressed much. One of them is quotient polymorphism. Support for quotient GADTs. At the moment, quotient types and GADTs don't operate well with one another, so that's something I would like to look into more in the future. Improved reasoning with, or actual reasoning with function extensionality. Currently, Liquid Haskell has an extension for function extensionality, but it doesn't operate well at the moment with quotient types, which can be a problem when you're defining, say, types that are, say, uncountable. You have an uncountable number of strictly positive positions or something like this. Interoperability with the type class refinement. So again, Liquid Haskell has a refinements for type classes that you can add, but this doesn't operate well with Quotient Haskell at the moment. In particular, it would be nice if the specification of a type class happened to match what was required by a quotient type, that this would be automatically verified for you, but this currently can't be done, or at least for things that I've checked. And some improved error reporting in Quotient Haskell would be nice. And I think that's everything. I think I'm at the end of my talk.
Right behind you.
Thanks. Thanks for the talk. What happens from a user point of view if, on pencil and paper, I know that my function is respectful, but the SMT solver can't do it. So what happens next?
So there's a feature I haven't described here. There is a feature for being able to do manual proof obligations in circumstances like that that will extend what you're able to do. However, if you can't even do it via that at the moment, you just won't be able to define that function. But there are some circumstances where you can make use of manual proofs. However, for the use cases I gave here, such as the examples I gave there at the end, lots of functions I've defined on those, lots of common ones that you would define, those work perfectly well. So there's a large range of use cases, and some of them are described in the paper too that work.
So that's good to know.
Yeah.
Thank you for the nice talk. Quotient types are really important, so it's nice to see that we're moving towards getting them in Liquid Haskell. You gave this long list of examples. One was bags, which is very nice, so that says you can permute the elements. But often one also wants to get sets, where you collapse two elements. Does that work in your system or not?
Absolutely, yeah. Yeah. So actually the entire what's known as the Bohm hierarchy, that entire hierarchy works very well.
And then do you also get the subtyping?
Yes, right. You get the subtyping rules down the entire hierarchy. The reason that I actually wanted quotient polymorphism is because at the moment, something that's frustrating when you do this is that you have to redefine the map function for every single one of these things because they occur in both contravariant and covariant position. And so you need to keep redefining the map function for each one of the thing down the hierarchy. So quotient polymorphism would be nice to avoid that in the future.
So have you done that, or that's your next step?
That was one of the areas of further work. Yeah, that's something to continue work with.
Please do. That sounds great.
Yeah.
And then the other question I was going to ask is the other way these are used is for alpha equivalents in lambda terms rather than eta equivalents.
That's right.
Does that one work?
Yes, that also works. That was one of the examples, right?
Oh, no, I didn't see it, but they've taken your examples away. I believe you. It's an example in the paper. I will go read it. This is great. Thank you.
Yeah.
Yeah, we've got time.
Yeah.
Thank you for the talk. Very cool. I was curious if you had thought about supports for Haskell records and having sort of field accessors as special cases of functions which are not quotient respecting, and how you would have to handle that in the reasoning.
Sorry, could you repeat that, please?
Yes. So I was wondering if you had thought about support for Haskell record declarations, where you would get field accessor functions, which would then be a special case because there would be functions on quotient types which don't actually necessarily respect the quotiont, and you'd have to do some reasoning about them. Have you thought about what this would look like?
in that circumstance, they're just functions, right? They're not data constructors, so you wouldn't quotient them that way, right? Or if you did, you can quotient records just fine, but then if you quotient records, right, that's just like having a data type, just with, say, for example, a single constructor of all of the information in there. So, it's no different from just doing it this way. I don't necessarily understand the issue here.
No, because the field accessors are themselves then functions from the data type to some value, right? Are they quotient?
Yeah, but they would obey they would obey them by definition, right?
Oh, would they? Okay.
These. If I'm not sure I fully understand the problem here, to be honest.
We can discuss it later.
The x and y are reversible. Then pulling out x and y will give you a problem, just as you showed with.
Yeah, right, but that's not allowed. You wouldn't be able to do that. You wouldn't be able to access x and y because those functions don't obey the laws. That'd be like trying to say, okay, that'd be like trying to wrap something. So if you wrap something in a constructor and you say, okay, I'm not allowed to look inside, you say all of the values are the same, so I can't look inside. That'd be like trying to unwrap it. So that wouldn't be allowed. That's something that can be done, but you just wouldn't be able to use the accessors.
I think we have time for one more.
I got it. Sorry, it's a second question. You're providing quotients by, so to speak, arbitrary relations, right? But in mathematics, if I quotient by an arbitrary relation, and I've got two equivalence classes, one for x and one for y, and the equivalence classes are equal, that doesn't mean to say that x and y are related, but they're related by the equivalence relation generated by the relation effectiveness
right.
condition in quotients. So is that going on somewhere in Quotient Haskell under the hood? That
I mean, yeah, these types are just the effect. The terms now represent equivalence classes, right? You have equivalence classes of terms rather than.
yes, but if I start with a given, as a user, I feed in a given relation that I want a quotient by, I may need to then consider the equivalence relation generated by that. So is that something that
You want to access the actual end, like the total equivalence relation itself?
yeah. Well, when you're reasoning, you often have to, right?
I mean, all you really need to be able to access are the parts of it, right? The equality constructors. So you have, I mean, your equivalence relation is just built on top of the identity and the added equality constructors, so you can reason with those. Okay, I'm not sure I understand the.
All right. I think we're out of time, so maybe we can take the rest of the questions offline. Let's thank the speaker again.